Hello everyone, and welcome to Cisco Live 2020. My name is Sudha Kadgeri, and I thank you for joining me in my session on troubleshooting the next generation of wireless LAN controllers, namely the Catalyst 9800. Before we get into the technical content, a little bit about me. As I said, my name is Sudha Kadgeri. I have been with Cisco for over 14 years and currently work as a technical leader in Cisco's wireless support services, or what is commonly known as the Cisco TAC. I hold a wireless CCIE, but my true superpower is being a mom, an idea that is reinforced by my two little kids every single day. I'm the wifey in my house that keeps us the family tethered. Now, enough about me. Let's dive right in. In this session, we will be covering a lot of content. To make it easy for you guys to consume this, I have divided up the content into 4 chapters. In the first chapter, we will be talking about the hardware and software architecture of the 9800 series, along with looking at the life of a packet inside the box. In chapter 2, we will review the new config model along with other deployment considerations that would prevent any heartache and allow you for a smooth and successful deployment. Section 3, that's the meat of this session. We will look at the GUI troubleshooting dashboard on the 9800 as well as review all of the tracing and packet capturing capabilities available. Last but not the least, we will be looking at the health and KPI monitoring CLIs that are available and conclude with some key takeaways from this session. Let's get started. On the first up, just introducing how the debugging on the 9800 is. For the folks who are coming from the AOS world, the debugging here is entirely very different. We have a very simplified object model, and we operate on a store and process sort of debugging mechanism. If you recall from AOS, it was always about reproducing the issue to solve the problem. But in this case, we have always on logs and traces that allow us a lot of look back and the ability to also trace on failure. There have been a lot of improvements in terms of serviceability and traceability on the 9800 as opposed to the converged access or the AOS controllers. This is largely due to a very collaborative approach we have had since the inception of the product between the support services, TAC, folks out in the field, business unit, the engineering teams, test teams, and everyone involved. A large part of this collaboration has also come from our customers, whether these are the folks who are doing the early field trials or the customers who have deployed our products and provided us very useful feedback. So thank you, and we look forward to keep hearing from you. Now let's get into the architecture. As some of you might know, the 9800 is available in multiple form factors. A 9800 can be deployed on top of an access point, can be deployed on a Catalyst 9K series switch. It is also available as appliances, and it can be virtualized either on a private cloud environment like the KVM or ESXi or Hyper-V, or it can be deployed on public cloud environments such as the Amazon Web Services or Google Cloud. Now, all of these different form factors can be categorized into 3 main architectures or 3 main hardware architectures. This slide really gives you just a view into the different form factors along with the some scale numbers. The takeaway here should be that depending on the model that you are deploying, you may have to look very closely at what are the AP modes supported and therefore deploy accordingly. Now, as I mentioned, all the form factors can be categorized into 3 specific hardware architectures. The first and the one that will be discussed heavily in this particular session is the Cisco Packet Processor or the CPP-based data plane form factors. This includes all of the appliances, the 9800L, 9840, 9880, and also the virtual platforms, whether you deploy it in public or private cloud environment, it all remains the same. As you can see, essentially, all that really changes is the number of ASICs that are involved in data forwarding. So when I say CPP, this is essentially referring to the data plane or the chipsets involved with forwarding the data traffic and thereby achieving the performance and the scale numbers that we talked about. On a 9840, you would have one ASIC called the quantum flow processor. On the 9880, there is two. On a 9800 CL, it is virtualized in software. There is differences in CPU throughput, etc. The key takeaway here should be even though the 9800 CL provides a lot of scale, it has throughput limitation of 2 Gbps, which means you will need to look very closely at your sort of environment and look at which particular appliance or deployment would be the most appropriate for you. There's also a distinction in the certificates used between the appliances on the 9800 CL, but we'll talk about it a little bit here. Now, if you were to open up a 9840, this is how it would look like. The physical ports where you plug in your cables, connect into a port ASIC, which buffers all the traffic that comes in. There's a pass-through chip that has been inherited over from the ASI architecture, but it does not really do anything for wireless. There is a crypto chip available to do some DTLS operations, but all traffic goes from the port ASIC towards the QFP or the data plane, which in turn makes a decision whether it's just data traffic that it needs to do forwarding on, or if it is control traffic that it needs to hand over to the CPU complex. Now, the second type of architecture that is available is the FED or Doppler-based data plane architecture. This is essentially the Catalyst switches. This is the architecture that the Catalyst switches are based off of. The software and the control plane is no different when it comes to the 9800 between CPP or the FED and Doppler-based data planes. In case of a CPP, you would have CPP client programming the QFP, whereas in here you would have the FED driver programming the Doppler ASIC. But this is a session that will not really be discussing this particular architecture in detail. There's another Cisco Live session mentioned that goes into far more detail. So please refer to that if this particular platform is of interest to you. One thing, key takeaway here would be that the controller and switch, they are not two separate entities. When you do deploy the 9800 on the switch, it uses the same CLI, same web UI, and it is all integrated together. The last hardware architecture we have is where we deploy the embedded wireless controller on the access point. Now, primarily, this is an access point, so that all the hardware and the data plane is supplied by the access point itself. This is only supported on the 9100 series access point. With the access point, each model of access point provides slightly different data plane and Linux kernel on it. So it's not a one-to-one or the same thing between each of the platforms. So just be aware of it. While the EWC code in itself can, or the 9800 code can itself only be run on the 9100 platforms, there are subordinate APs that we support, be it Wave 2 or 11AX, that can join the embedded wireless controller. Now, as always on a COS AP, we have two partitions in the flash for primary and second and backup AP image, but we also distribute the EWC code and config and logs and traces between these two partitions. As I mentioned, the hardware and the data plane is provided by COS, and the software is only implemented as a container, or the controller is only implemented as a container. Now for some quick tips. The 9800 appliances come with a lot of different field upgradable parts. So it is recommended that you deploy the latest FPGA or ROM code that is published to take advantage of all the fixes that we may have, firmware fixes that are available in that code. Secondly, the uplink ports or the distribution ports on the 9840, it is generally recommended that you configure them as trunks. You have the option to configure them as a layer 3 port, but configuring layer 3 port and using that at wireless management is not recommended. So the ideal condition would be to set up these uplinks as trunks. And what you would do on the connected switch port would be to have spanning tree port first trunk enabled, so to allow for faster convergence. Now, There's only a handful of SFPs that are supported on these platforms. Please be sure to check the datasheet because in the newer codes, without a supported SFP, the link itself will not come up. In addition to the distribution ports, the 9800 appliances has an out-of-band management gig port called the service port. Now, typically on the 9800, we do not support VRFs, but the gig one port by itself comes by default in the management interface VRF. It's not really a big deal because this is just an out-of-band management port. All it needs to provide access is via HTTP, HTTPS, and SSH. So that it does perfectly fine as long as you provide the path or the route out the service port. As long as you build that static route connection, then you will be fine. However, the service port is not does not work very well when it comes to netcom telemetry, so please do not use it when integrating with the DNA center or prime infrastructure. As I mentioned, the wireless management interface, it is recommended it is a SVI with the trunk on the port rather than L3 port. 9800 appliances, they ship with the manufacturing installed certificate out of the factory. This is what gets used for all of the AP join and mobility tunnel bring up and any sort of detailless communication. So there really is no need to generate any other cell science certificates on it, nor to manually go line up some a certificate trust point with the wireless management interface. All of that is automatically done on the appliance. Which is very different than what the 9800 CL is like. So let's talk about the CL a little bit. I already mentioned there is a throughput limitation. So when you're deploying your network, you need to closely look at what sort of throughput would you expect on your uplink. Now, when you're deploying on the AWS or Google Cloud for that matter, you should when it comes to functionality such as reachability issues, it's very hard to troubleshoot in that environment. So don't expect much of an RCA. You might be recommended to just have to redeploy the box. So just be aware of it. Now on the 9800 CL, there is already an throughput limitation, right? So it does show up with this gigabit Ethernet interface context, but if your VNIC allows, you can make it 10 gigabit Ethernet by setting the speed. No harm done. It does not change the fact that there is still those throughput limits to deal with. Now, as I mentioned before, the 9800 appliances come with a manufacturer install certificate, but on the CL, it's simply a software, so there is no manufacturing involved. Therefore, whenever you have a 9800, one of the first steps you will be required to do is generate a self-signed certificate, which will allow for then the APs to join. Now, there is you can either use the day0 wizard to generate the cert or use the CLI mentioned. The part of one thing you will have to remember is the SSC generation makes use of the host name and it ties the cert to the wireless management interface, which means anytime you change the host name or the wireless management interface, you will need to regenerate the cert. There are some other quirks around how you deploy the 9800 CL. One of them is you will have to enable force transmits. Typically, to avoid MAC impersonation, force transmit is recommended to be disabled on VMs. But in this case, it will prevent the client from communicating, since the hundreds and thousands of clients that are behind the controller will not really be learned by the vSwitch. It will prevent the traffic forwarding, and we don't want that. So you will have to enable force transmit. The other thing you need to enable is promiscuous mode. Now, the drawback with enabling promiscuous mode is if all the VMs that are in the same port group and that are handling the same traffic, same VLANs will end up receiving each other's traffic. So it is very important that when you deploy the 9800 VMs, you make sure that they are aligned with a different physical port or different VLAN so as to avoid overwhelming them. One such example is from the lab here. As you can see, the 9800 CL is on a promiscuous mode, but its CPU utilization keeps spiking up to 60% because there are other VMs deployed in the same port group. Now, ESXi 6.7 should and later should have the capability to learn MAC addresses, but we haven't seen that interplay with having how the forged transmits need to be set up. So those still apply. Hyper-V is one deployment where promiscuous mode is not required. So that's a cool thing there. Now, when bootstrapping the 9800 CL, you have a couple of configuration options. One of them is how to configure the management or out-of-band service port. So please do not use DHCP because it ends up creating a default route of the service port and causing all the traffic to leave the service port instead of the typical expected uplinks. So try and avoid that. Also from 17.3 onwards, the 9800 CL have a 16 GB requirement, so you can't just resize it, you'll have to actually redeploy the 9800 CL. Talking about the software architecture, ISXE is the software that runs on the 9800 platforms. Basically, this is nothing more than this is ISXE code is based on binary OS or BinOS, which is nothing more than the Linux kernel with some custom Cisco patches. What the Linux kernel allows us to do is implement all the processes that we have as Linux daemons, as process daemons. So what was the classic iOS functionality can now be implemented as an iOS daemon. There has been effort made over a period of several years now to take away this monolithic blob that iOS was, extract some of the functionality out of it, and re-implement it as separate processes. So things like DHCP or .NET, all of which was performed by iOS, now sit outside of the iOS. In addition, because it is this process-based implementation, we have the opportunity to have wireless implemented as hosted apps, which is what has been done for 9800. Now, ISXE, there's two trains that exist for it. There's a 16.x train, there's a 17.x train. Both of them refer to the same binary OS for the 9800. Now, 16.x trains have been available for a few years now. The early 16.1 up to 16.9 are only supported on switches and routers. The first code that supports the 9800 would be 16.10.1. Now we have had a few codes in there. As I mentioned in the beginning, this session we will be primarily focusing all of our content out of the 16.12 4A and the 17.31 release, which came out within the last month. Now, the AP model supported. On the 9800, we do support some 11AC Wave 1, specifically the 17, 27, and 3700 APs, but not a whole lot more. We do support all of the Wave 2 and 11X APs and some IoT APs. Now, a lot of this hardware support got added in a staggered manner, so it's not like day one of the release all of this was supported. So you will have to validate which AP is supported in which particular code when deploying. So make use of the release notes to get that information. Also, the same holds true for the AP modes. While local mode and flex connect has been supported from day one, features such as mesh and flex plus mesh have come up have been enabled on different AP platforms and different code versions. So again, depending on your deployment, please make sure you read the wireless compatibility matrix, which has all of that information and much more. If you're using an SDA deployment, something that we are not really discussing in this session, but if you have an SDA deployment with the DNA center, please refer to the SDA compatibility matrix. Now, typically, compatibility is a guideline, but it is not strict, except in the 9800, where there are some guidelines which are much stricter, as in it's a one-to-one mapping on what the table mentions. It's not that if I say prime infrastructure 3.8 supports 17.2, meaning everything up to PI 3.8 is supported. That's not how it is. It's actually a one-to-one mapping. So if it says use a certain version of prime infrastructure, or CMX, or DNA center, or so on with the 9800, please try and stick closely to it. Otherwise, you will see some unexpected outcomes. Now let's get to the process architecture itself. Here's the data plane which we inherited from what we discussed in the hardware architecture, right? This is the ASIC that comes shipped out of the box, or it might be a virtual one. On top of it is the Linux kernel. So again, BinOS is Linux kernel plus Cisco patches, which is why we have the Linux kernel. And we already had some of the ISXE infra items. So if you look at a switch or a router ever before the 9800 came into being, all of them would already have all of these entities in place. All we did for the 9800 was go ahead and add wireless processors on top of it. So we have the main process under wireless is what is called the WNCD. As you can see, there are multiple instances of it. We'll talk about it in a second. There are also other wireless processes like RRM Manager and MSPD or Mobility and so on, which are implemented. But all of these are one instance of the process, not multiple like WNCD. So all of these are processes that the kernel communicates with directly. Now you have the processes and you have the data plane and you, but how do you talk to them? Now on the 9800, each of the process has a leverages a database of its by itself. Meaning all of the configuration that the WNCD manages for AP connectivity or client connectivity is saved in the form of a database. All of the operational data is also tracked as a database. Because each of the process has its own database, of course, we are going to need a database manager. So we have two of them. One, there is a database manager that is more involved with the config data and system information, whereas we also have an operational data manager that is more into the statistics and the state of the particular AP client or the mobility tunnel. So the two data managers exist. Since the DBM is responsible primarily for all the configuration handling, any uh, northbound management system that you use to write to the box, whether it's the CLI, whether it's the web UI, prime infrastructure, DNA center, or even if you use some sort of open programmability model, the open programmability might go through the DMI processes, but eventually they all end up writing into DBM, which is then responsible for distributing the information over to WNCD and retrieving from WNCD. There is also another entity called REPM. It stands for Replication Manager, as the name suggests. It's more relevant in the scenarios where we have to replicate traffic or where there's HA or high availability involved. So now that the 9800 is built, here's some acronyms for your reference. Let's take a closer look at what is WNCD. So WNCD, it stands for Wireless Network Control Daemon. Essentially, that is the most important wireless process there is in the system. It is responsible for all AP CAPWAP tunnel termination as well as for all client traffic termination. Now, unlike all the other processes, the WNCD is going to have multiple instances, what we call the horizontal scaling. It is because we have these multiple instances, we can provide the sort of AP and client scale that we have. Because there are multiple instances, we also have a WNC manager daemon that handles the communication between the WNCD device instances. Now, each instance, as I've already mentioned previously, has its own database that will keep its own configuration data and operational data. Now, digging down deep further into the WNCD, WNCD is responsible for all of the AP communication. So you will have submodules for CAPWAP, you will have submodules for .11 and AAA and IP-Learn and Policy Manager, which are all involved with getting the client up in registered state. In case of an SDA, there is some Lisp involved as well before AP or a client gets onboarded, and that communication is also initiated by the WNCD. On a quick note on the EWC architecture, as I said, it's implemented as a container. Now, this is a very low scale deployment, right? So it's not going to have as many wireless processes as we talked about. Obviously, it doesn't have as many WNCD instances. It doesn't need it to support the scale that it does support. So on the EWC, we only have one WNCD. There is a lot of ISXC infra processes that are disabled, like the FMAN-FP, FMAN-IP. None of those come into play because there is no CPP to program. Also, unlike other platforms where each process has its own DB, there is actually only a single DB on the container to which all the wireless processes write. In addition, we have some ISD punt injector infra, and the new entity that is introduced is what is called an EWC shim, and we'll see its use in a couple of minutes here. Now, again, to quickly summarize, APCOS provides the data plane and it provides the Linux-based operating system, or the access point runs the APCOS Linux-based operating system. In a given deployment, if you have multiple 91xx APs, you only need one of the APs to run the controller code. The others will simply be subordinate APs to the EWC. The only mode that is supported is Flex Connect, and like I said, there's a fewer processors and therefore a single DB on EWC. Let's take a quick look at the packet flow inside the box. Now, this is a picture you're familiar with. Packet enters from the port, it gets buffered at the port ASIC. It passes through the Astro because Astro is not really doing any manipulation to it. It comes up to the QFP. A QFP looks at the packet and decides, is this a control packet or a data packet? Since we're looking at control plane, it is going to punt the packet up to the CPU. So again, the packet flow would be enter, get punted to kernel sends it to the WNCD, which does its processing, sends the response back and gives it back to the kernel and goes out the data plane. Now there's certain terminology associated with all that is happening. When a packet comes into the data plane, is handed over to the control plane or WNCD in this example, then it is called punting of the traffic, or it's called the punt path. WNCD, after it has done its processing, will synchronously respond and inject the response packet back into the Linux kernel and outpost through the data plane. Asynchronously, WNCD also will be doing other communication, or for that matter, any process you had would have other communication that it has to do. It would have to communicate with other processes like ISD in this case, so an inter-process communication channel exists. Also, the control plane is responsible for ensuring the data plane gets programmed with any entity that the WNCD learns about. So for example, if an AP joins, that AP entry has to get programmed through the various software components down to the data plane so that any AP traffic gets hardware forwarded versus being punted up to the CPU. Same goes for all client traffic. So asynchronously, the WNCD will also communicate with F1IP, with F1IP to inform it of any new AP it has learned about or the client it has learned about. IP in turn will sequentially communicate with the F1FP, which in turn talks to the CPP client or Fed in case of a catalyst switch, which will then go ahead and program the data plane. Once the programming is done on the data plane, all traffic that is entering the system, all the data traffic that is entering the system will simply be handled by the QFP and returned to the network without involving the CPU. On a quick note, on the EWC side, the way the packet flow works is when a packet comes in, the data plane first makes a decision whether the packet belongs to the controller, the access point, by looking at its IP address. So EWC is one of those where the access point has its own IP address, but the controller container that is deployed will also have to be defined, an IP will have to be defined even for that container. So if the traffic is meant for IP2, it is simply punted over to the AP processes. If the packet comes in with a destination of IP1, depending on the UDP ports involved in the packet, if it has to do with CAPAP or if it has to do with RRM, there is a preset defined list of UDP ports or DCP ports for which the packet is punted over to the wireless processes. Any traffic that is meant for IP1 but is not for one of the predefined ports automatically is assumed to be meant for ISD and it gets punted that way. Now, the purpose of EWC shim is because here we are using the AP kernel, not really the controller kernel. So all of the Linux BNOS Linux kernel customizations we don't have that opportunity. We don't have those here. Therefore, we need some sort of an entity to take the packet that is being sent from the network and format it to a way that the ISD can consume. So the purpose of EWC shim is essentially to translate the packet to that method. With that, we are at the end of this chapter. Thank you for listening. See you in the next chapter to discuss the new config model.